This video is going to look at proving trig identities. Proving trig identities is really just doing a question like simplifying trig identities, except that you know what the answer is. So it's nice because you know what your answer is. The issue with a proof is that you need to show your work, you need to justify your steps mathematically, and you need to make it in a neat, readable mathematical argument. You need to remember your algebra, and you need to make sure that you don't violate any rules of mathematics. So when we're doing a trig proof, what we want to do is start with one side of the equation. We want to show steps, which may include any of the following, that will manipulate the equation to look exactly like the other side of the equation. It doesn't matter if you work from the left side to the right side or the right side to the left side. We could be doing algebraic manipulations, add, subtract, multiply, divide. We could be doing substitutions with identities that we know from your formula sheet, converting expressions into terms of sine and cosine, combining fractions, multiplying by conjugates, factoring, things like that. You know you're finished when both sides of the equation look identical. So again, it's nice because it's really a problem where you know what the answer is. You just have to justify your work mathematically. All right, so let's take a look at this one. We're going to prove tangent of x plus cotangent of x equals secant of x times cosecant of x. So first I graphed this just to prove to you that it is an identity statement. Remember, an identity statement, that is a statement that is true regardless of what value we put in for x. So when we graph an identity statement, both sides of the equal sign will give me the exact same graph. So you can see here we got the same graph. So I want to do this proof. So remember, I'm going to start with one side of the equal sign, and I'm going to make it look like the other side by doing some mathematical manipulations. I would always start with the side that looks more complicated or contains addition or subtraction signs. So in this case, my left side contains an addition subtraction sign, so I'm going to start with that side. It's always possible to work either way. One way just might be easier than the other. And typically if you start with the side that has addition or subtraction signs, you can combine those terms together and that might help you out. So I'm going to start with my left side here. And the first thing that I want to look for is if I have some secants, cosecants, tangents, or cotangents, I'm going to rewrite them using their basic definitions. So those basic identities. So I'm going to rewrite tangent as sine of x over cosine of x. And then I'm going to rewrite cotangent as cosine of x over the sine of x. I'm not going to change the other side of the equation, so I'm just going to leave that secant x times cosecant x. Next, I notice that I have two fractions here that I'm adding together, and I remember that in order to add or subtract fractions, I need common denominators. So what I'm going to do is rewrite both of these fractions with a common denominator, and my common denominator is going to be cosine times sine. So in this first fraction, I need to multiply by sine of x over sine of x. And in the second fraction, I'm going to multiply by cosine of x over cosine of x. So remember, multiplying by sine over sine or cosine over cosine is really just multiplying by 1. So it's just changing the form of the fraction and not the value. So then on this first side, I'm going to get sine squared of x over sine x times cosine x plus, and then my second fraction is going to give me cosine squared x over sine x times cosine x. And then again, I'm not going to change the other side. Typically, if we don't change the other side, we just write the equal sign and leave it blank. But you can continue to rewrite it every time if you want. Now on the left side, I have two fractions with a common denominator, so I can combine this together. So now I'm going to get sine squared x plus cosine squared x over my common denominator, which is sine x times cosine x. And then again, I'm not changing the other side. Now I'm going to use my Pythagorean identity, and my numerator, sine squared plus cosine squared of any angle, is going to give me 1. So this is 1 over sine x times cosine x. So remember, what we're trying to get it to look like is secant x times cosecant of x. I know those are reciprocal functions, so now I'm just going to rewrite this side one other way here. So I'm going to write this as 1 over cosine x times 1 over sine x. So I'm just splitting that fraction up, and I'm switching the order around. 1 over cosine x is the same as secant of x times 1 over sine of x is equal to cosecant of x. And that's exactly what we had on the other side of the equal sign. So now I know that my proof is done. Both sides of the equal sign look identical. Okay, here's another example. So we have 1 over secant x minus 1 plus 1 over secant x plus 1 equals 2 times cotangent x times cosecant x. So again, I can start on either side. I like to start on the side that has addition subtraction on it because usually that allows me to combine into one particular fraction. So again, what I'm starting with here needs a common denominator. So remember, these entire terms are what I have to look for a common denominator with. So my common denominator is going to just be secant x minus 1 times secant x plus 1. So we have 1 over secant x minus 1 plus 1 over secant x plus 1, and that's what I started with. And then on this first fraction, I have to have the secant x plus 1, so I'm going to multiply by secant of x plus 1. So if I do that in the denominator, we also have to do that in the numerator. And then I'm going to do similarly over here. I've got the secant x plus 1, but I need the secant x minus 1. So if I multiply it to the denominator, I have to multiply it to the numerator. And then my other side I'm not changing, so I'm just going to leave that. Okay, so now I'm going to just try to simplify these. So this is going to give me secant x plus 1 times 1 just gives me that over secant x plus 1 times secant x minus 1 plus, and then over here I've got just secant x minus 1 over, again, my common denominator, which is secant x plus 1 times secant x minus 1. And I'm not changing the other side at all. Now I have a common denominator, so I can go ahead and add these two fractions. So I have a secant x plus 1 plus a secant x minus 1, which is going to give me 2 secant x. And then the plus 1 and the minus 1 are going to cancel out. So I just have 2 secant x over my common denominator. I'm also going to go ahead and multiply these two conjugates out, which is going to give me secant squared x. And then the minus secant x and plus secant x will cancel out, and then I have a plus 1 times a minus 1, so minus 1. And again, still not changing the other side. So now I've combined this into one fraction, which is better than what I started with, which was two different fractions. And now at this point, I'm going to go and look at my formula sheet, and I'm going to see that I have a formula for secant squared of x. So secant squared of x is equivalent to 1 plus tangent squared of x. So I'm going to do that substitution. So I've got 2 secant x, and then I'm going to substitute in for secant squared x, 1 plus tangent squared x, and then I still have the minus 1 here. So then here the plus 1 and the minus 1 are going to cancel out, and we have 2 secant x over tan squared of x. So this is looking better. I have a 2 on both sides now. I need a cotangent and a cosecant, and right now I have a secant over cotangent squared. So now I'm just going to kind of separate these out. I have a 2, then I have a secant of x, and then I have a 1 over tan squared x. So I'm just separating those. And then 1 over tangent squared is actually cotangent squared, so 2 secant of x times cotangent squared of x. Okay, so again, we're getting closer. So I've got the cotangent, but I've got squared here, but not over here, and I've got a secant here, but a cosecant over here. So again, I'm just going to kind of rewrite this. I'm going to write 2 cotangent x times cotangent x, so I'm just, instead of writing the squared, I'm writing it out twice, times secant x. And then we've got 2 cotangent x, cosecant x still on the other side. So now I'm just going to do a little bit of work with this cotangent times secant. So I'm going to leave the 2 cotangent x by itself. And then cotangent is the same as cosine x over sine x. So I'm using the basic definition. And secant is 1 over cosine x. So then those cosine x's cancel out. Then we have 2 cotangent of x times 1 over sine of x. And I know 1 over sine of x is actually cosecant of x. So I have 2 cotangent x cosecant of x, which is what we had on the other side. So again, I know my proof is done because the two sides look exactly identical. All right, so here I've got another example. I have cosine x over 1 minus sine x equals 1 plus sine x over cosine x. So my steps that I would try to look at would be, are there any substitutions I can make from my formula sheet? And in this case, there's not. Are there any secants, cosecants, cotangents that I can substitute with their basic definitions, and in this case there's not. Is there any fractions that I can add, or is there any algebra I can do? And again, in this case, there's not really anything I can do. But what I want you to notice is that each of these fractions has a binomial term. So we have 1 minus sine x on the left and 1 plus sine x on the right. So if you have a binomial term and there's nothing else to do, I want you to think that I can use the conjugate. So we have a binomial term with no other sort of procedures that I can do. So we're going to multiply by the conjugate. Both of the other examples, I started with the left side and worked to the right side. So just on this one, I'm going to start on the right side and work to the left. It doesn't matter. I can do it either way, but just to show you that it will work in either direction. So here I'm going to leave the left side alone. And then on the right side, I've got 1 plus sine of x over cosine of x. And then remember, my goal was to multiply by the conjugate. So the conjugate of 1 plus sine x is 1 minus sine x. So if I do it to the numerator, I have to do it to the denominator. So then again, I'm going to leave the left side alone, so I'm just going to write the equal sign. So here I'm going to go ahead and multiply out this numerator. So we're going to have 1, the minus sine x and plus sine x are going to cancel out, and then minus sine squared of x over, and then my denominator is just cosine x times 1 minus sine of x. Okay, so now 1 minus sine squared x, when you see a squared term with an addition or subtraction sign, remember you're going to think of Pythagorean identities. So if you look at your Pythagorean identities, 1 minus sine squared x is really the same as the cosine squared of x. So we have cosine squared of x over cosine of x times 1 minus sine of x. And then this cosine can cancel with one of these, and then I'm left with cosine of x over 1 minus sine of x, which is exactly what we had on the other side. So my left and right sides look identical, and I know that my proof is completed. All right, one more example here. We've got cotangent squared x over 1 plus cosecant of x equals cosecant x minus 1. So again, I'm going to start with the left side because this side looks more complicated. So here what I'm going to start with is I have a cotangent squared and I have a 1 plus cosecant squared. So cotangent squared is on my formula sheet with my Pythagorean identities. So remember, your identity statement from your formula sheet is cotangent squared theta plus 1 equals cosecant squared of theta. So here I have cotangent squared by itself. So again, if we just say, okay, I can just manipulate that, this would be cosecant squared of theta minus 1. So I'm going to use this substitution over here with the cotangent squared. So I'm going to rewrite this cosecant squared of x minus 1 over 1 plus cosecant of x equals, and then I'm not going to change this other side, so I'm just going to leave that. Now what I want you to notice is that in your numerator you have a difference of 2 perfect squares. And remember when we did our simplifying trig expressions, we talked about difference of 2 perfect squares, a squared minus b squared factors into a plus b and a minus b. So when you see that difference of 2 perfect squares, you probably want to go ahead and factor it. So this is going to give me cosecant x minus 1 times cosecant of x plus 1. And then my denominator is 1 plus cosecant of x, so I'm just going to switch the order of that around and make it cosecant of x plus 1. Because addition's commutative, I know I can do that. And then I can cancel these two whole terms, and I'm left with cosecant of x minus 1, which is exactly what I had on the other side. So I know my proof is done again.